name is Gus Ellerm. I'm a PhD candidate from the University of Canterbury. I've just started my postdoc at the University of Auckland down in New Zealand. And I'm here to talk to you about some of my PhD research, which is a framework called Life Application, which is all about collecting and integrating automated computational pipelines with our research articles, generating live representations of our research. Next slide. So to begin, I thought I'd provide a bird's eye view of what we're doing here. So Life Application is a framework that embeds computational processes with our research articles, and by doing so, enables systematic changes in the articles themselves. We can conceptualize Life Application within 3 layers. From bottom to top, we have the infrastructure and hardware, which captures things like scientific tools, instruments, HPC, federated and distributed compute. This layer is abstracted by the workflow orchestration layer, which involves workflow management systems such as Globus Flows, which we'll talk about today, CWL, and Pegasus. These orchestrate our processes across infrastructure and hardware with workflows. And finally, there's the programmatic article layer, where a programmatic article is an article that can be manipulated as an object or a DAG, or a set of hierarchical nodes, which we can evaluate against a set of criterion to determine their inclusion or exclusion or other sort of dynamic content behaviors. For this presentation, I'm going to be focusing on some of the work that we've done with Globus Compute and Globus Flows within these workflow orchestration layers, and how we can containerize information from the execution of these systems for embedding and decision-making in the programmatic article layer. When approaching the integration of Globus Flows with the Life Application framework, we identified 3 minimal infrastructure patterns that we'd like to support. The first uses custom action providers, which are sort of the most flexible tool for extending Globus Flows with some custom behaviors. The second uses Globus Compute for supporting a general compute interface for users. And the final one is just a mixture of the two. So what we're looking to do here is enable robust workflow executions that could be re-executed either based on triggers or timers over long periods of time, as well as across federated or distributed environments, taking into account security and collaborative flow management techniques. So given we have some minimal targets for our Globus Flows infrastructure, we need to design an interface that integrates this workflow management system with our programmatic articles. To do this, we lean on workflow provenance information, where provenance is a record of a workflow's execution containing information regarding data flows, produced or consumed data, methods used, and states that the flow terminates within. To generalize provenance information within Life Application, we standardize the provenance records generated during a workflow management execution. And this standardization means that we can, with a little extra work, provide interoperability between the programmatic article layer and the workflow orchestration layer, meaning we could potentially switch out the workflow management system for another or the programmatic article technology for another, given that it's producing provenance to the standard. The provenance record itself represents discrete runs of a workflow, including its inputs and outputs, formal parameters, and authored domain metadata. Workflow provenance can come in various flavors depending on the required specificity of the record, how much detail is retained regarding that flow's execution. For our application here, we wanted to extend a current provenance information standard using prior wisdom. The workflow run RO-crate standards are a set of provenance run models that define provenance information with varying levels of granularity. They extend the RO-crate standard, which describes how we can containerize digital research objects alongside structured metadata. There are 3 profiles within the standard. There's the process run crate, the workflow run crate, and provenance run crate. Each of these extend the last with additional provenance information. For Life Application, what we're interested in are sort of the most descriptive provenance representations. So we're using the provenance run crate, which describes the workflow's execution, formal parameters, and data flows, as well as the discrete steps that were executed within that flow itself. We've made some custom modifications to the provenance run crate spec, primarily facilitating its deployment on distributed infrastructure, such as the flows infrastructure that we're targeting. And generally, you can think of each distributed step orchestrated in a flow as being responsible for generating its own subset of provenance information. We call that subset of information the distributed step crate, which is on the right, which needs to be encoded at runtime. Once a flow has run to a completion state, these distributed step crates are collected and collated into the final provenance record. So to enable this provenance architecture within Globus Flows and Globus Compute, we needed to extend Globus Compute to generate these distributed step crates. We also need to manage the resulting provenance information in the system to create the final provenance record. It's relatively simple to extend Globus Compute with some custom logic. We edit the helper script, which is invoked on each incoming job, and wrap the execution of that job with some metadata embeddings. This gives us access to some hardware performance metrics, the executed function, input and output data, and some contextual information about the user and the compute environment. Finally, we write the distributed step crates to disk with the name set to the UUID of the executing job, and we use that UUID when building the final provenance record. Right, so now we have some Globus Compute node generating distributed step crates that we need to manage, preferably with minimal user input. To do this, we extend Gladia, which is a Python SDK that abstracts some of the more complex flow definition writing tasks away from users. Using this framework, we created a new class of tool definition, a Provenance tool, which is a normal Globus Compute tool defined within Gladia, but when generating the Globus Flow definition, it automatically adds transfers and check steps to the flow definition, which facilitates the movement of distributed step crates to a management server somewhere. So putting this all together, we have a Globus Flows with compute architecture that generates discrete provenance information in the form of distributed step crates, automatically manages that resulting provenance information and transfers it to a management server, which then collates our final provenance record, which we call the orchestration crate in the image over here. And then this orchestration crate is ready for handoff to the programmatic article layer for use in some dynamic document format. I'd end on a video if it will play. I'll have to leave this up to your imaginations. What happens is that we execute a flow using this infrastructure. It generates an orchestration crate, and then that orchestration crate is ingested by a Quarto document, which is sort of a Jupyter notebook-esque technology, which interfaces with our orchestration crate and makes some decisions based off its content, depending on the intermediate and immediate data that were recorded during the execution of the flow. So that's things like decisions regarding terminology used, conclusions drawn, and semantic markup of the document.